What is up, team, and welcome back to another video. This, I think, is the first video of our second semester. There will be some more specifically on notes posted up by the end of this week, kind of recapping what we've done so far. But this is going to be the first one in terms of skills quiz solutions. So last week we took a skills quiz, and I want to go over the answers. So let's do this a couple different ways. We'll start with number one, obviously. And the purpose of number one was finding the cosine, sine, and tangent of this image, specifically of this theta, this angle here on this triangle. The first thing I would do to answer a question like this is understand the positioning of the sides in terms of uh, the labeling. And so if we have an angle here, um, we know for sure that anything across from a 90-degree angle in a right triangle is going to be the hypotenuse. Okay, the hypotenuse. And then once the hypotenuse is labeled, the other two sides, could either be the opposite or the adjacent. So the opposite side is always going to be, whoa, what happened to the pen? The opposite is always going to be right across from theta all the way across. I'm going to like to put that word here, across from theta. And then your adjacent side is always next to that theta. So this is the adjacent side or next to. If you notice from class, I always use the same colors. Even in college, I had, back in school, I used to have the same colors going on so that way I could label anything that I needed to. And then using this, it's easier for me to then um, apply now the SOHCAHTOA piece to find the proper ratios for each of these. So if I go ahead, I'm going to come down here. I'm going to answer it down here. For number one, if I remember, I have SOHCAHTOA, which is a clever rhyme for us to remember, but it's useless, effectively useless, if we have no idea what it stands for. So the SO piece, we have the sine of some theta is equal to the ratio of the sides of the opposite and the hypotenuse sides. Okay, co or SOHCA is cosine of theta, and that has the relationship of the adjacent side and the hypotenuse. Okay, and then TOA ultimately is the tangent function, tangent of theta, and that's the opposite over the adjacent. Okay, and then now using these, all we have to do is just plug in the numbers that we have. So for the first one, I'm going to use an orange pen today. We have sine of theta is going to equal the opposite value, which is 9, boop, over the hypotenuse, which is 15. So that's all I was looking for this problem is, do you understand how to organize the values in a triangle to discover what sine, cosine, and tangent are? The next one, we're going to have 12 over 15 using the adjacent side, and then ultimately tangent of theta equals the opposite 9 over the adjacent, which is 12. Okay. So doing something like this gets you to the point where you don't really need to simplify anything if you don't want to. You can. All of these are able to simplify. That's great. However, we don't need to for the purpose of this problem. I just wanted to see if you can recognize that. Okay. Number two, I'm going to do it just right here off to the side. Number two, using this triangle, I want to find the value of x. Well, in order to do that, I need to go back and do the same thing that I did on the other side, or for number one, and label all of the sides. So across from the 90-degree identification marker, we're going to have the hypotenuse. If we go across from the theta, or in this case, it's labeled as 24, we're going to have an opposite side. And then right next to that theta, our angle of interest, this theta, we're going to be having the adjacent side. So in this problem, if we take a look, we have theta, which is equal to 24 degrees. So I always like to label it out. We have the adjacent side, which is equal to x, and we have the hypotenuse, which is equal to 11. Oops. And then we don't have an opposite side. That value is not given to us. Okay. And so because there's nothing there, and I look at this and I have the adjacent and hypotenuse, actually I can go back to the first problem and I can find which function here will help me use these two values in my problem solving process. Well, cosine is the only one that utilizes the adjacent and hypotenuse. So over here, I'm going to pick cosine of theta because I have values for those, adjacent over hypotenuse, and then I can proceed to start plugging in all of my parts. So I'm going to have cosine of 24 degrees equals x over 11. Okay. Go ahead and zoom out a little bit. So now that I've plugged in all the pieces, kind of like a puzzle, I could start doing a couple different ways of problem solving. For this specific problem, I'll actually show you I'm going to do the cross multiplication type of method. And to make this a little bit more of a shortcut, if there's nothing in the denominator or there's not a fraction over on the other side, and you're starting to become comfortable with your math skills, you can recognize this as just a 1, and all you need to do is just multiply the denominator of the other side to whatever value is over here. So that's effectively saying we're going to be multiplying 11 with both sides. Okay, and so when you do that, we end up with the value. Let me go with it a little bit thinner. 11 times cosine of 24 degrees. Now, the way that we spoke about it in class, I taught you kind of the cross multiplication way. It's foolproof, and you understand kind of how and why we're doing it. But in this case, it's the same exact solution if we multiply out the 11 from one side. Okay. So then if we keep the 11 multiplied with, I'm going to put a set of parentheses here while I give us the simplified version of cosine of 24. And that value is effectively going to be 0.9135. And now on my calculator, I'm going to use the whole value here because I have it available to me. And so whenever you have a complete decimal value, or as complete as you can, I would always use that. Okay. And then I'm just going to press the multiplication button times 11 on my calculator, and I get 10.049, but I'm going to round that up to 10.05 equals x. And that is my final answer for this piece. Okay. So first two problems down. I'm not going to say not too bad, but sometimes we get a little confused if we don't organize ourselves in a way that is helpful. So if you try to find your one method of starting problems and then apply that to most of the problems that you're going to be going through, then you won't have a hard time going through this stuff. Okay, but those are your first two answers. The third one's where we get interesting. Okay, this is where we actually can do a couple different things to answer this question. So number 3 says, and actually what I'm going to do here is summarize the problem so I can come down on the screen a little bit. Oops. So there's a Ferris wheel. I put a Ferris wheel up there as a reference for us so that way you can use. But we wanted to find the height, number 3. We wanted to find the height at the 10 o'clock position of the Ferris wheel. Okay, we're going to assume that the Ferris wheel has a height of 25 feet from the center to the ground. In class, we called that value d, which is the distance from the center of the wheel to the ground, and we called this 25 feet in this problem. This value of d will change depending on what kind of Ferris wheel we're working with. And then r is going to be the radius of the Ferris wheel, which is really important because you'll see in the next problem I give you the diameter, not the radius. So you got to think about it a little bit more intently. Okay, so here are two of our numeric values, and then we have a position at the 10 o'clock position that we're trying to find the height for. So in this problem, what would be nice for us to also know is the theta that we are going to be using. And There's two different thetas that we would use in this problem. So let me see if I can get a circle here. Um, if we mark off the 12 o'clock position, the 3 o'clock position, the 9 o'clock position, and we look at the 6 o'clock position, 3 o'clock and 6 o'clock position, we may remember the circle or the unit circle that we made in class that represented 3 o'clock as 0 degrees for us. 12 o'clock was 90 degrees. 9 o'clock was 180 degrees. And then 6 o'clock was 270. Oops. Okay. Those are my actual angles. So the orange are going to be, I'm going to call them actual angles. Okay, we want a theta to use. So orange is like our actual angles, and then for the blue, if we remember that we wanted to keep our reference plane, which is this x-axis, intact, we wanted to then find what theta was at any given point in reference to this axis. And so when we did that, we looked at same kind of deal. So 0 degrees for the reference, 90 degrees for the 12 o'clock position, but we came over here and now 180 became 0 degrees because we're not extending above the x-axis at all. And then the reference for the 6 o'clock position was also 90 degrees. So take a look at those notes in the Google Slides to review kind of what we're talking about here. And while you're at it, take a look at also what the other values are for the different points on this Ferris wheel. So if I come over here and I have the 9 o'clock position, 10 o'clock position, and 11 o'clock position, there's two ways for us to actually look at this. The first way is going to be using an actual angle beginning at the 3 o'clock position. So 3 o'clock, we said that because the Ferris wheel is a circle and has 360 degrees to travel a complete turn, if we divide that by the 12 different positions, then that means each position to travel from for example, the 3 o'clock position to the 2 o'clock position would be a value of 30 degrees between positions. And so there's two ways for us to think about it. The first way is going through the actual angle of this 10 o'clock position to figure out what the heck it is. So what I'm going to do here is I'm going to go ahead. I'm going to erase all this stuff really quick. I'm going to rewrite it so that way it looks a little bit neater. It's a little messy right now. Okay, so we have the 3 o'clock position, the 9 o'clock position, the 12 o'clock position, the 1 o'clock position, and the 2 o'clock position. I don't want to have everything below for right now. I don't want to just keep cluttering the screen. But if we go ahead and we take a look at this, the 3 o'clock position will have a value of 0 degrees. That's where we're starting. Now, if we were to go straight to the 10 o'clock position and identify this angle here, this complete actual angle, we'll see that we traveled one set of 30 degrees, two sets of 30 degrees, three sets of 30 degrees. We already said that 12 o'clock is 90. And then we added two more, which mean this 10 o'clock position means that our theta value is going to equal 150 degrees. This is for our actual angle. Okay, and you can use this to problem solve, or you can use something called the reference angle. Now, having this picture is really nice because whatever is left over to the x-axis is considered our reference angle. And so theta would also be able to represent this, however much is left over, 30 degrees. Okay, so the reference is actually how much is left over after the actual angle is already discovered in reference to the x-axis. Now, we are using reference angles to the x-axis. Now, you can use reference angles to the y-axis, and then I'll give you something a little bit different. But in this type of problem, we will be using reference to the x-axis. So it's the closest distance down to the x-axis. Okay. So using either of these values, you can plug into our formulas that I have up here for you. So you have the reference angles equals the height, or I guess the height is equal to d plus or minus the r sine of theta. Just you need to know whether or not you're going to be above or below that center line. Or we can start getting easier or more efficient and use the actual angles to find something using the actual function for sine. So in this, what I'm going to do is I'm going to use the actual angles, so that means I'm going to be using f of theta for the actual angles equals d plus r times sine of theta. And in this problem, because I'm dealing with my actual angles, I'm going to be plugging in 150 to represent my actual angle. So here, if I go to start the problem, I'm going to get f of 150. That's what our function is going to be evaluated at, equals our d value is 25 plus our radius is 10 multiplied with the sine of 150. Okay. So I just plugged in all the values from that point, and now you can go ahead and evaluate. So this means that f of 150 degrees is going to equal 25 plus 10 times. Every time I evaluate some sort of trig function, I always put it in a set of parentheses. It's just good practice because sometimes we just get so caught up in the problem solving, we forget what part of numbers are associated with other parts of numbers, and sometimes our work gets confusing. But that value of sine of 150 degrees is going to equal 0.5 or a half, which means I get 25 plus 10 times a half. Well, half of 10 is 5. Then I can continue to simplify using PEMDAS, and I get 30. So this is great, but 30 doesn't tell me what my actual answer is. So I'm going to go ahead. I'm going to use this to write the actual answer. At the 10 o'clock position, we are 30 feet above the ground. And with that, that will be our answer. Okay. It's always nice to make sure you summarize what the answer is going to look like for any of these problems. Okay. So there's the answer for that one. Number 4 follows a similar pattern, or I guess a similar problem-solving technique. However, it just has a little bit more of trickiness when it comes to the problem itself. So number 4 says, assume a Ferris wheel has a diameter of 32 feet. The height from the 12 o'clock position to the ground is 40 feet. And this Ferris wheel also moves at a rate of 12 degrees per second. So not only do we have some different information, but it's also moving. Okay. How high off the ground is somebody who is 3 seconds past the 3 o'clock position? So let's go ahead and let's summarize that first piece. Okay, so we're here, we want to find the height at 3 seconds past the 3 o'clock position. Okay, so this ultimately we need some sort of theta, and so we need to figure out what theta is to answer that question. We also know that it's 40 feet to get to the ground. So from the 12 o'clock position, it's 40 feet to the ground. Well, that's not D yet because D is from the center to the ground. This is a different value, so we need to think about this. And it gave us the diameter of the Ferris wheel is going to be 32 feet. So we got a little bit of different problems here. So we have a diameter, we have a position from the 12 o'clock position. Oh, and we forgot the rate, 12 degrees per second. So if you remember the homework assignment, this is the angular speed, 12 degrees per second. And how are we going to use all this information to actually get us to the point where we can start problem solving? Well, first thing I highly recommend is you draw like a little diagram for yourself. So here I'm just going to draw a nice, beautiful, perfect circle to represent a Ferris wheel and just give it some legs to go to the ground. And now this Ferris wheel is not going to be accurate at all in terms of proportional measurements, but it's always nice to have some sort of illustration. So let's see. From the We're going to need to know the 3 o'clock position, which we've already referred to as 0 degrees. It's our reference angle. It's like kind of like our starting point. And then we want 3 seconds past. So we don't know where that's going to be yet. So I'm just going to say here. And then this distance is going to be seconds, 3 of them. And we want to know what this value is. So we'll find that in just a moment. Okay. Let's see what else we know. We know from the 12 o'clock position, it's 40 feet to the ground. So from this point, from the 12 o'clock position to the ground here, that position is going to be 40 feet, which is important because that means my height can't be above 40 feet. 40. And then finally, we're given the diameter of the Ferris wheel is 32 feet. Well, if we just take this right away and we know that the radius is 1/2 of the diameter, then we can go ahead and find this. 1/2 of 32 feet is 16 feet. So the radius value for this specific Ferris wheel is going to be 16 feet. Okay. Now, if we take a moment and to think about this, do we have all the parts we need? Let's check this out. I'm going to use the same formula as before, the one using the actual angles. The actual angle, which is D plus R times sine of theta. Okay, so if we remember, our D value is going to be the distance to the ground from the center. Okay, from the center. We don't know that yet. Okay, and then R is going to be our radius, and then theta is going to be our actual angle. So how do we proceed with problem solving? Well, looking at this problem, we know the radius. Okay, so I'm going to start rewriting this and filling it in with the pieces that we know. So we know F of theta equals D plus, okay, the radius is 16. So we have part of this equation for us to solve for, which is nice, but we still don't know the distance from the center to the ground, and that's something we need to discover. So using this diagram and using the information that we have, we know that this whole distance is 40 feet. Well, according to the problem, it was given to us that the diameter is 32. So if we look at this and identify, or I guess mark, from the 12 o'clock position down to the 6 o'clock position, that whole distance is going to be 32 feet. It's the diameter of the circle, which means that we're left with a small little sliver from the bottom of the Ferris wheel, from the 6 o'clock position to the ground, as 8 feet. Well, if we draw another circle, I'm going to just say like another model for us, then that means from the center to the 6 o'clock position, because that's the radius of this image or of our Ferris wheel, that's 16 feet. The remaining portion that's left to the ground that we still need is going to represent a value of 8 feet. Actually, let's do black. This little sliver is 8 feet. So according to this problem, if I go like this, there's our Ferris wheel. This distance is a value of d. That's what we want. Well, in total, this gives us a complete value of 24 feet. So this problem was a little bit harder because I needed to take into consideration the radius, the diameter, and the remaining height off the ground that we did not have before. So this 24 is now our new value for D. We had to deconstruct the problem a little bit. Okay, so I'm going to replace it up there. 24. Now, the last part is theta. How do I find the actual angle? Well, this one's not as hard because the problem actually tells you how many seconds passed a certain position. Well, we know that the 3 o'clock position represents 0 degrees. So if we start from 0 degrees and then 3 seconds have passed, each one of those seconds represents a certain amount of rotation. So let me actually draw this a little bit differently. We got 1 second, 2 seconds, 3 seconds. 1, 2, 3 seconds. You don't need to draw it like this. This is just how I visualize it. That's a 12-degree rotation, 12-degree rotation, 12-degree rotation. That's a 20, 12-degree rotation. And each time we're going to be increasing that amount, we end up with 0, because that's our starting point, 12, 12, 12, which means we have gone 36 degrees in rotation of this Ferris wheel. So if I take that 36 degrees, let me go ahead and go like this. I'll write that over here. 3 seconds past 3 o'clock is the same as 3 seconds past 0 degrees, which is the same as 36 degrees past 0 degrees, which equals 36 degrees. Then we can start plugging in all of our values. We have f of 36 degrees equals 24 plus 16 sine of 36 degrees. And using this information, it's a lot easier for us to now simplify the problem to get a solution. So we get f of 36 degrees equals 24 plus 16 multiplied with, always put the set of parentheses there, 36 degrees. Sine of 36 is 0.5877. And like I said before, on my calculator, I'm going to use that whole decimal value that is given to me. Then I get 24 plus 16 times that value, which is 9.404. Once again, I'm going to use the whole decimal value that's given to me on my calculator. This is just to show some work. Equals 24 plus that value, which now my calculator does not want to work, plus 24 is going to be a value of 33.404. And now, remember, this isn't our answer yet. We got to say 3 seconds past 3 o'clock. We are 33.404 feet above the ground. And that is our solution. Okay, so the last one's a little tricky. You just got to take into consideration a lot of different moving parts. But for that, that was the solution to this problem. See if I can zoom out. Boom and boom. Those are the solutions. Everything in orange is kind of like the work that I'm looking for, kind of the stuff that you're going through. Depending on how you got there, it's up to you. You get a little bit of a creative freedom there, but I do look for the work that you're uh, proceeding through. And if you take a look, most of it is anchored around the trig functions. Okay, so being able to recognize what trig function to use, when to use it, and using it appropriately will determine kind of your points on this quiz. Okay. And so for that, if you have any questions, bring them to class. But for now, you're free to go. Have a good day, and I'll see you next time.